What if the universe itself is connected in ways that defy everything we think we know about space and time? Imagine two particles separated by billions of light years, yet somehow instantly influencing each other's behavior. This isn't science fiction, it's quantum entanglement, one of the most baffling and fascinating phenomena in all of physics. Welcome to a journey through 30 mind-bending theories about the universe's quantum entanglement, where the rules of reality as we know them seem to unravel. From Einstein's famous skepticism to the possibility of wormholes linking entangled particles, we're about to explore the strange, the speculative, and the downright astonishing. Why does this matter? Because quantum entanglement isn't just a quirky quirk of physics. It challenges our very understanding of existence, space, and time. So, if you're ready to dive into a world where particles communicate faster than light, where the universe might be a hologram, and where the fabric of reality itself might be stitched together by invisible quantum threads, stay with us. By the end of this video, you'll not only grasp the basics of quantum entanglement, but also uncover theories that could change the way you see the cosmos forever. Let's begin. Now, let's step into the world of one of the greatest minds in physics, Albert Einstein. Even he was baffled by quantum entanglement, famously calling it spooky action at a distance. But why did Einstein, a pioneer of modern physics, find this phenomenon so unsettling? At its core, quantum entanglement seemed to defy the very principles he had established with his theory of relativity. According to relativity, nothing can travel faster than the speed of light. Yet, entangled particles appear to communicate instantaneously, no matter how far apart they are. This instant connection, Einstein argued, couldn't possibly be real without violating the laws of physics as we know them. To challenge this idea, Einstein, along with physicists Boris Podolsky and Nathan Rosen, proposed what's now known as the EPR paradox. They argued that if quantum mechanics were complete, it would imply that particles could influence each other faster than light, which they believed was impossible. Instead, they suggested that there must be hidden variables, unknown factors, that determine the behavior of particles in a way that didn't require this spooky connection. The EPR paradox was a direct challenge to the foundations of quantum mechanics, sparking decades of debate and experimentation. But here's the twist: experiments later showed that Einstein's hidden variables didn't exist. Quantum entanglement was real, and particles really could be connected in ways that defied classical physics. So, while Einstein's skepticism was understandable, it turns out the universe is even stranger than he imagined. This spooky action at a distance isn't just a quirk. It's a fundamental feature of reality, one that continues to push the boundaries of our understanding. And as we'll see next, this discovery opened the door to even more mind-bending theories about the nature of the universe. Now, let's turn our attention to a pivotal moment in the history of quantum physics: John Bell's groundbreaking work. While Einstein's skepticism about quantum entanglement sparked a fascinating debate, it was Bell who took the conversation to a whole new level. In the 1960s, Bell proposed a mathematical framework that would ultimately settle the question of hidden variables once and for all. His work centered around what's now known as Bell's theorem, a set of inequalities that tested whether hidden variables could explain the strange behavior of entangled particles. Here's how it works. Bell's theorem essentially created a way to measure whether particles were following hidden rules, as Einstein suggested, or if they were truly connected in a way that defied classical physics. If hidden variables existed, the results of certain experiments would stay within specific limits defined by Bell's inequalities. But if the results broke those limits, it would mean that entanglement was real, and that particles were communicating in ways that couldn't be explained by any hidden factors. When scientists finally put Bell's theorem to the test, the results were nothing short of astonishing. Experiment after experiment showed that entangled particles violated Bell's inequalities, proving that hidden variables couldn't explain their behavior. This was a monumental moment in physics. It confirmed that quantum entanglement wasn't just a theoretical curiosity, but a fundamental feature of the universe. Particles really could be connected across vast distances, instantly influencing each other in ways that defied our classical understanding of reality. But what does this mean for our understanding of the universe? Bell's work didn't just disprove hidden variables, it forced us to rethink the very nature of reality. If particles can be entangled, then the universe isn't as local or deterministic as we once thought. Instead, it's a place where connections can exist beyond space and time, where the act of measuring one particle can instantly affect another, no matter how far apart they are. This discovery has profound implications, not just for physics but for philosophy as well. It challenges us to consider whether the universe operates on principles that are far stranger and far more interconnected than we ever imagined. As we move forward, we'll explore how this idea of entanglement continues to shape our understanding of the cosmos, leading us to even more mind-bending theories about the fabric of reality itself. Now, let's take a closer look at one of the most mind-bending aspects of quantum mechanics, quantum superposition. This principle is at the heart of what makes quantum entanglement so strange and fascinating. At its core, superposition means that a particle, like an electron or photon, can exist in multiple states at once until it's observed or measured. Imagine flipping a coin. In our everyday world, it's either heads or tails. But in the quantum realm, that coin is spinning in mid-air, existing as both heads and tails simultaneously. It's only when you catch it and look that it decides which side to land on. This idea might sound like science fiction, but it's been proven time and time again through experiments. For example, in the famous double-slit experiment, particles like electrons behave as both particles and waves until they're observed. It's as if they're exploring all possible paths at once, only settling into a single state when someone or something measures them. This bizarre behavior is what makes superposition so central to quantum mechanics, and it's also what makes entanglement possible. Here's where things get even more intriguing. When particles become entangled, their states are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. But because of superposition, those states aren't fixed until the moment of measurement. Think of it like this. Imagine you have two entangled coins, each spinning in mid-air. They're connected in such a way that if one lands on heads, the other will instantly land on tails, even if they're on opposite sides of the universe. But until you look at them, both coins are still in that fuzzy, in-between state of being both heads and tails at the same time. This connection between superposition and entanglement is what makes quantum mechanics so different from the classical physics we're used to. In our everyday world, objects have definite properties. A chair is solid, a ball is round, and so on. But in the quantum world, particles exist in a kind of probability cloud, with their properties only becoming definite when observed. And when those particles are entangled, their fates are intertwined in ways that defy our classical understanding of space and time. So, what does this mean for our understanding of reality? It suggests that the universe operates on a level far stranger than we can easily comprehend. Superposition and entanglement together paint a picture of a reality where particles are not just individual entities but part of a deeply interconnected web, where the act of observation plays a crucial role in shaping what we see. As we continue to explore these ideas, we'll uncover even more astonishing theories about the nature of the universe, theories that challenge everything we thought we knew about how reality works. Now, let's step into one of the most fascinating and mind-expanding theories in quantum mechanics, the many worlds interpretation. This idea takes the strangeness of quantum superposition and entanglement and pushes it to an entirely new level. According to this theory, every time a quantum event occurs, like the measurement of a particle in superposition, the universe doesn't just settle on one outcome. Instead, it splits into multiple parallel universes, each representing a different possible outcome. Think of it like this. Imagine you're standing at a crossroads, and every decision you make creates a new version of reality. In one universe, you turn left, in another, you turn right. The many worlds interpretation applies this idea to the quantum realm. When a particle is in superposition existing in multiple states at once, the act of measuring it doesn't collapse it into a single state. Instead, the universe branches into multiple realities, each one corresponding to a different possible state of the particle. This theory offers a bold solution to some of the paradoxes of quantum entanglement. For example, when two entangled particles are measured, their states are instantly correlated, no matter how far apart they are. In the many worlds view, this isn't because of some mysterious faster-than-light connection. Instead, it's because every possible outcome of the measurement already exists in its own separate universe. The particles aren't communicating across space, they're simply part of a vast multiverse where every possible outcome is realized. What does this mean for our understanding of reality? It suggests that the universe is far more complex and interconnected than we ever imagined. Every quantum event, no matter how small, could be spawning countless new universes, each one slightly different from the last. This idea challenges our classical notion of a single, linear reality and replaces it with a sprawling, ever-expanding multiverse. But the many worlds interpretation isn't without its critics. Some argue that it's an extravagant solution, creating an infinite number of universes to explain what could be simpler phenomena. Others question whether it's even possible to test or prove the existence of these parallel worlds. Still, for many physicists, the theory offers an elegant way to make sense of the strange behavior of quantum systems without invoking the need for an observer to collapse the wave function. As we continue to explore the implications of this theory, one thing becomes clear: the universe is far stranger and more wondrous than we ever imagined. The many worlds interpretation invites us to consider a reality where every choice, every event, and every quantum interaction creates a new branch in the cosmic tree of existence. And as we'll see next, this idea ties into even more astonishing theories about the nature of reality and the multiverse. Now, let's shift our focus to another groundbreaking theory that offers a completely different perspective on quantum entanglement: the Copenhagen interpretation. Unlike the many worlds interpretation, which suggests that every quantum event spawns new universes, the Copenhagen interpretation takes a more restrained approach. At its core, this theory proposes that quantum systems remain in a state of superposition, existing in multiple states simultaneously until they are observed. It's only at the moment of observation that the system collapses into a single, definite state. To put it simply, imagine a coin spinning in the air. While it's spinning, it's neither heads nor tails, it's in a superposition of both. But the moment you catch it and look, it lands on one side. The Copenhagen interpretation applies this idea to the quantum world. Particles like electrons or photons don't choose a state until they're measured. Until then, they exist in a fuzzy, undefined state of possibilities. So, how does this interpretation handle quantum entanglement? Let's revisit our entangled particles. When two particles are entangled, their states are deeply connected, no matter how far apart they are. According to the Copenhagen interpretation, the act of measuring one particle instantly determines the state of the other, even if they're light years apart. This might sound like faster-than-light communication, but it's not. Instead, the measurement itself causes the entangled system to collapse into a specific state, resolving the superposition for both particles simultaneously. This brings us to one of the most intriguing aspects of the Copenhagen interpretation: the role of the observer. In this view, the observer isn't just a passive bystander, they play an active role in shaping reality. The act of measurement is what forces the quantum system to make up its mind and settle on a single outcome. This idea has sparked endless debates about the nature of reality and whether it exists independently of observation. Some argue that this interpretation places too much importance on the observer, while others see it as a profound insight into the relationship between consciousness and the physical world. Critics of the Copenhagen interpretation often point to its reliance on the concept of wave function collapse, which some see as an ad hoc addition to quantum mechanics. Unlike the many worlds interpretation, which avoids collapse by branching into parallel universes, the Copenhagen interpretation leaves the mechanism of collapse somewhat mysterious. Yet, despite these criticisms, the Copenhagen interpretation remains one of the most widely taught and accepted frameworks in quantum physics, offering a practical and intuitive way to understand the behavior of quantum systems. As we compare these two interpretations, it's clear that they offer very different answers to the same fundamental questions. The many worlds interpretation paints a picture of an infinite multiverse, while the Copenhagen interpretation focuses on the here and now, emphasizing the role of observation in shaping reality. Both theories challenge our classical understanding of the universe, pushing us to rethink what it means to exist in a quantum world. Next, we'll explore another fascinating idea, quantum decoherence, and how it attempts to bridge the gap between these interpretations, offering new insights into the nature of quantum systems and their behavior. Now, let's turn our attention to a concept that helps us understand why the strange world of quantum mechanics doesn't always spill over into our everyday experiences: quantum decoherence. This theory offers a fascinating explanation for how quantum systems, which can exist in multiple states at once, eventually settle into the single, definite states we observe in the classical world. Quantum decoherence describes what happens when a quantum system interacts with its environment. Imagine you're trying to listen to a quiet conversation in a noisy room. The background noise makes it harder to focus on the conversation, and eventually the meaningful signal gets lost in the chaos. Similarly, when a quantum system like an entangled pair of particles interacts with its surroundings, the delicate superposition of states becomes noisy. The environment effectively measures the system, causing it to lose its quantum coherence and collapse into a single, observable state. This process helps explain why we don't see quantum weirdness in our macroscopic world. For example, a cat in Schrödinger's famous thought experiment can't realistically be both alive and dead at the same time because the cat is constantly interacting with its environment. These interactions cause the quantum superposition to break down, leaving us with a cat that's definitively alive or dead, not both. Quantum decoherence also has profound implications for quantum computing. In a quantum computer, information is stored in qubits, which rely on superposition and entanglement to perform complex calculations. However, if these qubits interact too much with their environment, they can lose their quantum properties through decoherence, leading to errors in computation. This is why quantum computers require extremely controlled environments, often cooled to near absolute zero, to minimize these interactions and maintain coherence. But quantum decoherence doesn't just solve practical problems. It also sheds light on the measurement problem in quantum mechanics. Remember how the Copenhagen interpretation relies on the idea of wave function collapse when a system is observed. Decoherence provides a more detailed explanation for why this collapse happens. Instead of invoking an observer, it shows how interactions with the environment naturally cause the system to choose a state. This doesn't completely eliminate the need for an observer, but it does offer a more physical explanation for how quantum systems transition from the quantum to the classical world. Critics of decoherence argue that it doesn't fully solve the measurement problem, as it still leaves open the question of why we perceive one outcome rather than another. However, it does provide a crucial bridge between the quantum and classical realms, helping us understand how the bizarre rules of quantum mechanics give way to the familiar laws of our everyday world. As we continue to explore the mysteries of quantum entanglement, quantum decoherence reminds us that the boundary between the quantum and classical worlds is not as sharp as it might seem. It's a reminder that even the strangest phenomena are shaped by their interactions with the world around them. Next, we'll dive into an even more mind-bending idea: the possibility that entangled particles might be connected by microscopic wormholes, as suggested by the ER=EPR conjecture. This theory could revolutionize our understanding of space, time, and the very fabric of reality. Now, let's venture into a theory that sounds like it's straight out of science fiction, but is grounded in cutting-edge physics: the idea that entangled particles might be connected by microscopic wormholes. This concept, known as the ER=EPR conjecture, proposes a deep and unexpected link between quantum entanglement and the fabric of spacetime itself. At first glance, quantum entanglement and wormholes seem like they belong to entirely different realms of physics. Quantum entanglement is a phenomenon where particles become so deeply connected that the state of one instantly influences the state of another, no matter how far apart they are. Wormholes, on the other hand, are hypothetical tunnels through spacetime that could, in theory, connect distant points in the universe. But what if these two ideas are actually two sides of the same coin? The ER=EPR conjecture suggests just that. The refers to Einstein and Rosen, who first proposed the idea of wormholes, also known as Einstein-Rosen bridges, in the context of general relativity. The EPR stands for Einstein, Podolsky, and Rosen, who famously questioned the completeness of quantum mechanics by introducing the concept of entanglement. The conjecture proposes that entangled particles are not just mysteriously linked, but are actually connected by tiny wormholes. In other words, entanglement might be a manifestation of spacetime itself being intricately woven together at the quantum level. This idea bridges two of the most fundamental but seemingly incompatible theories in physics: quantum mechanics and general relativity. Quantum mechanics governs the behavior of the very small, while general relativity describes the large-scale structure of the universe. For decades, physicists have struggled to unify these two frameworks into a single theory of quantum gravity. The ER=EPR conjecture offers a tantalizing hint at how this unification might work. It suggests that spacetime itself could emerge from the entanglement of quantum particles, with wormholes acting as the threads that stitch the fabric of reality together. But how does this work in practice? Imagine two entangled particles like a pair of electrons. According to this theory, the entanglement between them isn't just a mathematical connection. It's a physical one, mediated by a microscopic wormhole. This wormhole doesn't allow for faster-than-light travel or communication, but it does provide a geometric explanation for why entangled particles seem to know each other's states instantaneously. It's as if the particles are whispering to each other through a hidden tunnel in spacetime. This theory also has profound implications for our understanding of black holes. In the context of the ER=EPR conjecture, the information that falls into a black hole might not be lost forever, but could instead be encoded in the entanglement between particles inside and outside the black hole. This could help resolve the long-standing black hole information paradox, which questions whether information is truly destroyed when it enters a black hole. Of course, this idea is still highly speculative, and there's much we don't yet understand, but it represents a bold step toward reconciling the strange rules of quantum mechanics with the elegant geometry of general relativity. It challenges us to rethink not just entanglement, but the very nature of spacetime itself. As we continue to explore the mysteries of quantum entanglement, the ER=EPR conjecture reminds us that the universe is far stranger and more interconnected than we ever imagined. And with that, let's turn our attention to another mind-bending question. What if entanglement doesn't just connect particles across space, but also across time? Now, let's take a step into a realm where the boundaries of time itself seem to blur. Quantum entanglement and its potential to transcend not just space, but time as well. What if entangled particles aren't just connected across vast distances, but also across different moments in time? This idea challenges our understanding of causality and opens up a whole new dimension to the mystery of entanglement. Imagine two particles that become entangled not just in space but in time. This means that the state of one particle at a specific moment could influence the state of another particle at a different moment, even if those moments are separated by seconds, minutes, or even years. At first, this might sound like science fiction, but experiments have already begun to explore this possibility. One such experiment involved creating entangled photons and then measuring their states at different times. The results suggested that the entanglement persisted even when the measurements were made at moments separated by a noticeable time gap. This implies that entanglement isn't just a spatial phenomenon, it might also be a temporal one, linking particles across the fabric of time itself. But what does this mean for causality, the principle that cause must always precede effect? If entanglement can connect particles across time, does it mean that an effect could influence its own cause? This idea, known as retrocausality, has sparked intense debate among physicists. While it doesn't necessarily violate the laws of physics, it does force us to rethink how we understand cause and effect in the quantum world. To put it simply, if entanglement can transcend time, it suggests that the universe might be far more interconnected than we ever imagined. It's as if the past, present, and future are all woven together in a single, intricate tapestry, with entangled particles acting as the threads that bind them. This doesn't mean we can send messages back in time or change the past, but it does hint at a deeper, more fundamental connection between events that we once thought were entirely separate. The implications of this are profound. If entanglement can span time, it could offer new insights into the nature of reality itself. It might even help us understand how the universe maintains its coherence across vast stretches of space and time. And while this idea is still in its early stages, it's a reminder that the quantum world is full of surprises, ones that continue to challenge and inspire us. With this in mind, let's shift our focus to another fascinating aspect of entanglement, its role in the mysterious physics of black holes. How does quantum entanglement help us unravel the secrets of these cosmic giants? That's where our journey takes us next. Now, let's venture into the enigmatic world of black holes, where quantum entanglement takes on a role that could help us solve some of the universe's greatest mysteries. Black holes, those regions of spacetime where gravity is so intense that not even light can escape, have long puzzled scientists. But what if quantum entanglement holds the key to understanding their inner workings? One of the most intriguing connections between entanglement and black holes lies in Hawking radiation. Proposed by physicist Stephen Hawking, this phenomenon suggests that black holes aren't entirely black. Instead, they emit tiny amounts of radiation due to quantum effects near their event horizons. Here's where entanglement comes into play. The particles that escape as Hawking radiation are thought to be entangled with particles that fall into the black hole. This entanglement creates a delicate link between the inside and outside of the black hole, raising questions about what happens to information that gets swallowed by these cosmic giants. This brings us to the infamous black hole information paradox. According to quantum mechanics, information about the state of a system can never be completely lost. But if a black hole evaporates over time through Hawking radiation, what happens to all the information about the matter that fell into it? Does it vanish forever, or is it somehow preserved? Quantum entanglement might hold the answer. Some theories suggest that the entangled particles in Hawking radiation carry encoded information about the matter that entered the black hole, effectively preserving it even as the black hole evaporates. This idea has led to groundbreaking concepts like the holographic principle, which proposes that all the information about a black hole's contents could be encoded on its surface, much like a hologram. Entanglement, in this context, acts as the glue that connects the information inside the black hole to the radiation escaping it. If this is true, it would mean that black holes aren't the ultimate destroyers of information we once thought they were. Instead, they might be cosmic archivists storing information in ways we're only beginning to understand. Understanding the role of entanglement in black holes isn't just about solving a theoretical puzzle, it's about uncovering the fundamental nature of reality itself. It challenges our understanding of space, time, and information, and it could even help bridge the gap between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. As we continue to explore this fascinating intersection of quantum entanglement and black hole physics, one thing becomes clear: the universe is far more interconnected than we ever imagined. And with each discovery, we move closer to unraveling the secrets of these cosmic enigmas. With that in mind, let's turn our attention to another mind-bending idea: how quantum entanglement might be linked to the very fabric of consciousness itself. Could entanglement hold the key to understanding the mind-body problem? That's where our journey takes us next. Now, let's shift our focus to one of the most provocative and debated ideas in the realm of quantum physics: the possibility that consciousness itself might be intertwined with quantum entanglement. This theory pushes the boundaries of both science and philosophy, suggesting that the strange behavior of entangled particles could hold the key to understanding the nature of the mind. At the heart of this idea is the ORCH, or theory, short for orchestrated objective reduction, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that consciousness arises from quantum processes occurring within the brain's neurons, specifically within structures called microtubules. According to this theory, these microtubules act as tiny quantum computers, where entanglement and superposition play a role in generating conscious experience. In other words, our thoughts, feelings, and awareness might be the result of quantum events happening at the smallest scales of our biology. But this theory is far from universally accepted. Critics argue that the brain is too warm and noisy an environment for delicate quantum processes to occur without being disrupted. They point out that quantum effects are typically observed in highly controlled, ultra-cold settings, not in the messy, warm conditions of biological systems. Despite these challenges, ORCH remains a fascinating and bold attempt to bridge the gap between quantum physics and neuroscience. The implications of linking consciousness to quantum entanglement are profound. If true, it could revolutionize our understanding of the mind-body problem, the age-old question of how physical processes in the brain give rise to subjective experience. It might also suggest that consciousness is not just a byproduct of complex neural activity, but a fundamental feature of the universe, woven into the very fabric of reality through entanglement. This idea also opens the door to even more speculative possibilities. Could entanglement explain phenomena like intuition, telepathy, or even the sense of interconnectedness that many people report? While these ideas remain firmly in the realm of speculation, they highlight how quantum entanglement challenges our understanding of not just the physical world, but the nature of existence itself. As we explore these theories, it's important to approach them with both curiosity and skepticism. The connection between quantum entanglement and consciousness is still a highly controversial and unproven idea, but it serves as a reminder of how much we have yet to discover about the universe and ourselves. With that in mind, let's turn our attention to another groundbreaking concept: the holographic principle. Could the universe itself be a hologram? And if so, how does entanglement fit into this picture? That's where our journey takes us next. Now, let's venture into one of the most mind-bending ideas in modern physics: the holographic principle. This theory proposes that our universe might not be what it seems. Instead of being a three-dimensional space filled with objects, it could actually be a two-dimensional hologram, a projection of information encoded on a distant surface. Imagine the universe as a cosmic movie screen, where everything we see and experience is just a vivid, three-dimensional image emerging from a flat, two-dimensional surface. Sounds like science fiction, right? But this idea has deep roots in theoretical physics and could fundamentally change how we understand reality. At the core of the holographic principle is the concept that all the information about the universe, every star, every planet, every particle, can be encoded on a boundary like the edge of the universe. This idea first emerged from studies of black holes, where physicists discovered that the information about everything that falls into a black hole isn't lost but is instead stored on its surface, known as the event horizon. This led to the startling realization that the universe itself might operate in a similar way, with all the complexity we see being a projection from a simpler, lower-dimensional reality. So, where does quantum entanglement fit into this picture? It turns out, entanglement might be the glue that holds this holographic reality together. In a holographic universe, the connections between particles, those strange, instantaneous links we call entanglement, could be the threads that weave the fabric of reality. Think of it like this: if the universe is a hologram, entanglement is the process that ensures every part of the image stays connected, no matter how far apart the pieces seem to be. Without entanglement, the hologram would fall apart, and the universe as we know it would cease to exist. This idea has profound implications. If entanglement is the foundation of the holographic principle, it suggests that the universe is far more interconnected than we ever imagined. Every particle, every event, every moment in time could be linked in ways that transcend space and time. It also raises questions about the nature of information itself. Could the universe be, at its core, a vast network of entangled information? And if so, what does that mean for our understanding of existence? Of course, the holographic principle is still a theory, and much about it remains speculative. But it's a powerful framework that challenges our assumptions about reality and offers a new way to think about the role of entanglement in the cosmos. As we continue to explore this idea, we're reminded once again that the universe is far stranger and more interconnected than we ever imagined. With that in mind, let's turn our attention to another fascinating theory: the possibility that dark matter, the mysterious substance that makes up most of the universe's mass, might also be connected to quantum entanglement. What could this mean for our understanding of the cosmos? That's where we're headed next. Now, shifting our focus to another intriguing possibility, let's explore how quantum entanglement might be connected to one of the greatest mysteries in the universe: dark matter. Dark matter makes up about 85% of the universe's mass, yet it doesn't interact with light or ordinary matter in any way we can directly observe. It's invisible, but its gravitational effects are undeniable, shaping galaxies and holding the cosmos together. So, what if quantum entanglement holds the key to understanding this elusive substance? Some physicists have proposed that dark matter might interact through quantum entanglement, creating a hidden network of connections that we can't see but that influences the structure of the universe. Imagine dark matter particles as being entangled with each other across vast distances, forming an invisible web that guides the formation of galaxies and clusters. This entanglement could explain why dark matter seems to clump together in specific patterns, creating the cosmic scaffolding we observe today. But how could entanglement explain dark matter's invisibility? One idea is that dark matter particles are entangled in such a way that they don't interact with electromagnetic forces, making them undetectable by conventional means. Instead, their interactions might be purely quantum in nature, mediated by entanglement. This would mean that dark matter operates in a realm entirely separate from the particles we're familiar with, governed by rules we're only beginning to uncover. This theory also raises fascinating questions about the nature of dark matter itself. Could it be that dark matter isn't just a collection of individual particles, but a vast, interconnected system held together by entanglement? If so, this would suggest that the universe is even more deeply interconnected than we thought, with dark matter playing a crucial role in maintaining the cosmic balance. Of course, this is still a speculative idea, and much about dark matter remains unknown. But if entanglement is indeed at the heart of dark matter's behavior, it could revolutionize our understanding of the universe. It would mean that the same quantum phenomenon that connects particles across space and time might also be shaping the largest structures in the cosmos. As we continue to probe the mysteries of dark matter and quantum entanglement, we're reminded once again of how much we still have to learn about the universe. These two enigmatic forces, one shaping the cosmos on the grandest scales, the other governing the smallest particles, might be more closely linked than we ever imagined. And that's a thought worth pondering as we move forward in our exploration of the quantum universe. Now, let's take a step back in time, way back to the very beginning of the universe. The Big Bang is often described as the moment everything began, but what if quantum entanglement was there, quietly shaping the cosmos from its earliest moments? This brings us to an intriguing question. Could entanglement have played a role in the birth of the universe itself? One of the most puzzling features of the universe is the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This radiation is remarkably uniform, with only tiny fluctuations in temperature. But how did the universe achieve such uniformity? After all, regions of space that are now far apart were once close together, yet they seem to have been in sync, as if they were connected somehow. This is where quantum entanglement comes into play. Some scientists propose that entanglement might have been the cosmic glue that linked these distant regions during the universe's infancy. Imagine the early universe as a hot, dense soup of particles, all entangled with one another. As the universe expanded, these particles were pulled apart, but their entanglement remained, creating a kind of quantum connection across vast distances. This could explain why the cosmic microwave background is so uniform. Because those regions were once entangled, they share a common history, even if they're now light years apart. But entanglement's role in the Big Bang doesn't stop there. It might also help explain the tiny fluctuations in the cosmic microwave background, which eventually led to the formation of galaxies and large-scale structures in the universe. These fluctuations could be the result of quantum uncertainty, amplified by the rapid expansion of the universe. In other words, the seeds of everything we see today. Stars, galaxies, and even ourselves might have been planted by quantum entanglement in the first moments of the cosmos. This idea also raises a fascinating possibility. Entanglement might not just be a feature of the universe, it could be a fundamental part of its origin. If entanglement was present at the Big Bang, it could mean that the universe was born with a built-in interconnectedness, a quantum network that has persisted ever since. This would suggest that the universe is not just a collection of separate objects, but a deeply connected whole, with entanglement weaving the fabric of reality itself. Of course, these ideas are still speculative, and much about the Big Bang remains a mystery. But if entanglement did play a role in the universe's birth, it would fundamentally change how we understand the cosmos. It would mean that the same quantum phenomenon that connects particles across space and time today might have been there at the very beginning, shaping the universe into what it is now. As we explore these theories, we're reminded of how much we still have to learn about the universe's origins. The Big Bang might have been the starting point, but the story of the cosmos is far from over, and quantum entanglement could be one of its most important characters. So, as we continue our journey through the mysteries of the universe, let's keep in mind that the answers might lie in the quantum connections that have been there all along. Now, let's shift our focus to a concept that feels like it's straight out of science fiction: time travel. Could quantum entanglement, the phenomenon that connects particles across vast distances, also allow us to bridge the gap between different moments in time? This idea might sound far-fetched, but some scientists have speculated that entanglement could hold the key to manipulating time itself. At the heart of this theory is the idea that entanglement doesn't just link particles across space, it might also connect them across time. Imagine two particles that are entangled. If one particle is affected in the present, its entangled partner, even if it exists in the future or the past, could respond instantaneously. This raises the tantalizing possibility that entanglement could allow for communication or even travel between different points in time. One of the most intriguing aspects of this idea is its connection to the concept of closed time-like curves, hypothetical pathways in spacetime that loop back on themselves. In theory, these curves could allow an object or information to travel back in time. Some researchers have suggested that entangled particles might naturally follow such curves, creating a kind of quantum bridge between different moments in time. If this is true, entanglement could provide a mechanism for time travel, at least on a quantum scale. But before we get too excited, it's important to note that these ideas are highly speculative. While the math behind closed time-like curves and quantum entanglement is fascinating, there's no experimental evidence to suggest that time travel is possible, even at the quantum level. In fact, many physicists argue that the laws of physics, as we currently understand them, make time travel extremely unlikely. The concept of causality, the idea that cause must always precede effect, seems to stand in the way of any practical application of entanglement for time travel. That said, the idea of entanglement transcending time isn't entirely without merit. Experiments have shown that entangled particles can exhibit correlations that seem to defy our classical understanding of time. For example, in certain setups, the measurement of one particle appears to influence its entangled partner, even when the measurements are made in such a way that it's unclear which measurement happened first. This has led some to speculate that entanglement might operate outside the usual constraints of time, hinting at a deeper, more mysterious connection between quantum particles. If entanglement does have a role to play in time travel or communication across time, the implications would be profound. It could revolutionize our understanding of the universe, challenging our notions of cause and effect, and opening up entirely new possibilities for exploration and discovery. But for now, these ideas remain firmly in the realm of speculation, a fascinating intersection of quantum physics and the mysteries of time. As we ponder these possibilities, we're reminded of how much we still have to learn about the nature of reality. Quantum entanglement continues to push the boundaries of our understanding, challenging us to think beyond the limits of space and time. Whether or not entanglement will ever enable time travel, one thing is certain: it will keep us asking questions and exploring the unknown for years to come. Now, let's turn our attention to a concept that sounds like it's straight out of a futuristic sci-fi movie: quantum teleportation. While it might not involve beaming people across the galaxy, this phenomenon is no less astonishing. At its core, quantum teleportation relies on the strange and powerful connection of quantum entanglement to transfer information between particles instantaneously, no matter how far apart they are. Here's how it works. Imagine two particles that are entangled, meaning their properties are linked in such a way that measuring one instantly affects the other, even if they're light years apart. Quantum teleportation takes advantage of this link to send information from one particle to another without physically moving the information through the space between them. Instead, the information is essentially teleported from one location to another using the entangled connection as a bridge. The process begins with a third particle, which carries the information you want to teleport. By performing a specific set of measurements on this particle and one of the entangled pair, the information is encoded and transferred to the second entangled particle, effectively teleporting it across space. What's truly mind-blowing is that this happens instantaneously, defying our everyday understanding of how information travels. But what does this mean for the real world? Quantum teleportation has enormous potential, particularly in the fields of quantum computing and secure communication. In quantum computing, teleportation could allow for the rapid transfer of quantum information between different parts of a quantum computer, enabling faster and more efficient processing. This could revolutionize industries like cryptography, drug discovery, and artificial intelligence, where complex calculations are essential. In the realm of communication, quantum teleportation could pave the way for ultra-secure networks. Because the information is transferred instantaneously and relies on the unique properties of entangled particles, it would be nearly impossible for hackers to intercept or decode the data. This could lead to a new era of secure communication, protecting everything from financial transactions to government secrets. Of course, there are challenges to overcome. Quantum teleportation requires incredibly precise control over entangled particles, and maintaining their delicate quantum states over long distances is no small feat. But researchers are making significant strides, with experiments successfully teleporting information over hundreds of kilometers using satellites and fiber optic networks. As we explore the possibilities of quantum teleportation, we're reminded once again of how quantum entanglement continues to push the boundaries of what we thought was possible. While we may not be teleporting people anytime soon, the ability to instantly transfer information across vast distances could transform the way we live, work, and communicate. It's a thrilling glimpse into a future where the rules of physics as we know them are rewritten, and the impossible becomes reality. Now, let's shift our focus to a groundbreaking idea that could redefine the way we connect and communicate: the quantum internet. Unlike the internet we use today, which relies on classical bits to transmit information, the quantum internet would harness the power of quantum entanglement to create networks that are not only faster but also incredibly secure. This futuristic vision of connectivity is built on the strange and fascinating principles of quantum mechanics, and it promises to revolutionize everything from cybersecurity to global communication. At the heart of the quantum internet lies the concept of entanglement. As we've seen, entangled particles share a unique connection that allows them to instantly influence each other, no matter the distance. This property can be used to create quantum networks where information is transmitted in a way that's fundamentally different from traditional methods. Instead of sending data through cables or wireless signals, the quantum internet would use entangled particles to encode and transfer information. This means that data could be shared instantaneously and with unparalleled security, as any attempt to intercept or tamper with the information would immediately disrupt the entangled state, alerting users to the breach. One of the most exciting applications of the quantum internet is in the field of secure communication. Imagine a world where sensitive information, like financial transactions or government secrets, could be transmitted with absolute certainty that it couldn't be hacked or intercepted. This level of security is made possible by quantum key distribution, a method that uses entangled particles to create encryption keys that are virtually unbreakable. Even the most advanced supercomputers would struggle to crack these codes, making the quantum internet a game changer for cybersecurity. But the potential of the quantum internet goes beyond just security. It could also enable entirely new forms of communication and collaboration. For example, quantum networks could allow for the seamless integration of quantum computers, creating a global quantum computing grid. This would enable researchers and industries to tackle complex problems, from climate modeling to drug discovery, by pooling the power of quantum processors across the globe. The possibilities are as vast as they are transformative. Of course, building a quantum internet is no small feat. One of the biggest challenges is maintaining the delicate quantum states of entangled particles over long distances. Quantum systems are incredibly sensitive to their environment, and even the slightest interference can cause decoherence, effectively breaking the entanglement. To overcome this, scientists are exploring technologies like quantum repeaters, which can extend the range of entanglement by amplifying and relaying quantum signals. Another hurdle is the development of practical quantum devices, such as quantum routers and switches, that can reliably manage quantum information. Despite these challenges, progress is being made. Experiments have already demonstrated the successful transmission of quantum information over hundreds of kilometers using fiber optic networks and even satellites. These milestones bring us closer to the dream of a fully functional quantum internet, though it may still be years or even decades before this technology becomes a reality. As we look to the future, the quantum internet represents more than just a technological leap. It's a glimpse into a world where the boundaries of space and time are redefined by the strange rules of quantum mechanics. While the road ahead is filled with obstacles, the potential rewards are immense. A quantum internet could unlock new possibilities for innovation, security, and collaboration, reshaping our world in ways we can only begin to imagine. And as we continue to explore the mysteries of entanglement, we're reminded once again that the universe is far stranger and more exciting than we ever thought possible. Now, let's venture into one of the most mind-bending ideas in quantum physics, the possibility that entangled particles might be connected to parallel universes. This theory takes the already strange phenomenon of entanglement and pushes it into the realm of science fiction, suggesting that the mysterious link between particles could extend beyond our own universe. Could entangled particles be whispering secrets to their counterparts in alternate realities? Let's explore this fascinating idea and how it ties into the broader concept of the multiverse. At the heart of this theory is the idea that entanglement might not just connect particles across vast distances in our universe, but could also bridge the gap between different universes. According to the multiverse hypothesis, our universe is just one of countless others, each with its own unique set of physical laws and realities. In this framework, entangled particles could be seen as threads weaving through the fabric of these parallel worlds, creating a connection that defies our conventional understanding of space and time. One way to think about this is through the lens of the many worlds interpretation, which we touched on earlier. This interpretation suggests that every quantum event spawns a new universe, creating a branching tree of realities. If this is true, then entangled particles might not just be linked across space, but also across these branching timelines. In one universe, a particle might spin up, while in another, its entangled counterpart spins down. This could explain why entangled particles seem to know each other's states instantly. They're not just connected through space, but through the multiverse itself. But how does this tie into the multiverse hypothesis? If entangled particles are indeed connected to parallel universes, it could provide a new way to understand the strange behavior of quantum systems. For example, the randomness we observe in quantum mechanics might not be random at all. It could simply be the result of interactions between particles across different universes. This would mean that what we see as probability in our universe is actually the outcome of events unfolding in countless others. This idea also raises intriguing questions about the nature of reality itself. If entangled particles are linked to parallel universes, does that mean our universe is constantly interacting with others? Could we, in some way, detect or even influence these alternate realities? While these questions remain speculative, they highlight the profound implications of entanglement for our understanding of the cosmos. Of course, this theory is still in its early stages, and there's much we don't yet understand. Testing the idea that entanglement connects parallel universes is incredibly challenging, as it would require evidence that transcends our own reality. However, some physicists are exploring ways to probe these ideas through advanced experiments and theoretical models, pushing the boundaries of what we thought was possible. As we ponder the connection between entanglement and parallel universes, we're reminded once again of how quantum mechanics continues to challenge our understanding of reality. Whether or not entangled particles are truly linked to alternate worlds, this theory invites us to imagine a cosmos far more interconnected and far stranger than we ever dreamed. And as we continue to explore these ideas, we may find that the answers lie not just in our universe, but in the infinite tapestry of the multiverse. Now, let's shift our focus to a question that lies at the very heart of quantum mechanics. What does entanglement tell us about the nature of reality itself? This theory takes us beyond the physics lab and into the realm of philosophy, where the strange behavior of entangled particles forces us to rethink some of our most basic assumptions about how the universe works. Is reality fundamentally deterministic, following strict cause and effect rules, or is it probabilistic, governed by chance and uncertainty? Let's dive into this profound debate and see how entanglement might hold the key to answering this age-old question. At the core of this discussion is the tension between two competing views of the universe. On one hand, there's the deterministic perspective, which suggests that every event is the inevitable result of prior events, like a cosmic domino effect. If we could know the exact state of every particle in the universe, this view argues we could predict the future with perfect accuracy. On the other hand, there's the probabilistic view, which quantum mechanics seems to support. According to this perspective, the universe operates on probabilities, not certainties. Particles don't have definite properties until they're measured, and even then, their behavior is governed by chance. Entanglement plays a crucial role in this debate because it challenges the deterministic worldview in a profound way. When two particles are entangled, their properties are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to defy the idea that the universe operates on strict cause and effect rules. Instead, it suggests that reality might be fundamentally interconnected in ways we don't yet fully understand. But does this mean the universe is inherently probabilistic? Some physicists argue that entanglement supports the idea that reality is built on probabilities. After all, quantum mechanics tells us that particles exist in a superposition of states until they're observed, and the act of measurement collapses this superposition into a single outcome. This randomness, they say, is not a limitation of our knowledge but a fundamental feature of the universe itself. In this view, entanglement is a reminder that the cosmos is far more unpredictable and far more mysterious than we once thought. Others, however, propose that there might still be a deterministic explanation for entanglement. Hidden variable theories, for example, suggest that particles have underlying properties that determine their behavior, even if we can't directly observe them. While Bell's theorem has largely ruled out local hidden variables, some physicists continue to explore non-local versions of these theories, which could preserve determinism while accounting for entanglement. These ideas remain speculative, but they highlight the ongoing struggle to reconcile quantum mechanics with our intuitive sense of how the universe should work. This debate isn't just academic, it has profound implications for how we understand reality. If the universe is fundamentally probabilistic, it means that chance plays a central role in shaping everything from the behavior of particles to the evolution of galaxies. It also raises questions about free will and the nature of existence itself. On the other hand, if determinism holds true, even in a modified form, it suggests that the universe operates according to a deeper, hidden order that we're only beginning to glimpse. As we grapple with these questions, entanglement serves as a powerful reminder of how much we still have to learn about the cosmos. Whether reality is deterministic or probabilistic, one thing is clear: the universe is far stranger and more interconnected than we ever imagined. And as we continue to explore the mysteries of entanglement, we may find that the answers lie not just in the particles themselves, but in the very fabric of reality. Now, let's turn our attention to one of the most ambitious quests in modern physics, the search for a theory of quantum gravity. This theory aims to bridge the gap between quantum mechanics, which governs the tiny world of particles, and general relativity, which describes the vast cosmos of stars and galaxies. At the heart of this quest lies quantum entanglement, a phenomenon that might hold the key to unifying these two seemingly incompatible frameworks. Quantum mechanics and general relativity are the twin pillars of modern physics, but they operate in entirely different ways. Quantum mechanics deals with probabilities, uncertainty, and the strange behavior of particles at the smallest scales. General relativity, on the other hand, describes the smooth, curved fabric of spacetime and the force of gravity that shapes the universe on the largest scales. For decades, physicists have struggled to reconcile these two theories into a single, unified framework, and here's where entanglement comes into play. One of the leading candidates for a theory of quantum gravity is loop quantum gravity. This approach suggests that spacetime itself is made up of tiny, discrete loops woven together like a fabric. These loops are so small that they exist at the Planck scale, far beyond our current ability to observe. But here's the fascinating part: entanglement might be the glue that holds this fabric together. In loop quantum gravity, entangled particles could be connected through these spacetime loops, creating a network of relationships that define the structure of the universe itself. This idea suggests that entanglement isn't just a feature of particles, it's a fundamental property of spacetime. Another promising theory is string theory, which proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings can form different patterns, giving rise to the particles and forces we observe. String theory also suggests that spacetime has more dimensions than the 4 we're familiar with, up to 10 or even 11 in some versions. Entanglement plays a crucial role here too. Some physicists believe that entangled particles might be connected through these extra dimensions, creating a hidden web of relationships that could explain the unity of quantum mechanics and gravity. But why is entanglement so important in this context? Because it challenges our traditional notions of space and time. In both loop quantum gravity and string theory, entanglement suggests that the universe is far more interconnected than we once thought. It's not just that particles are linked across vast distances, it's that spacetime itself might be built on a foundation of quantum connections. This idea has profound implications for our understanding of reality. If entanglement is the key to quantum gravity, it means that the very fabric of the universe is woven together by quantum relationships, blurring the line between the microscopic and the cosmic. Of course, these theories are still in their early stages, and much work remains to be done. But the potential is staggering. If we can uncover the role of entanglement in quantum gravity, we might finally solve one of the greatest mysteries in physics: how the universe works at every scale, from the tiniest particles to the largest galaxies. And as we continue to explore this frontier, one thing is clear: entanglement isn't just a curiosity of quantum mechanics, it's a window into the deepest secrets of the cosmos. Now, let's shift our focus to a concept that touches the very essence of our existence: time. Specifically, the arrow of time, the idea that time flows in one direction from past to future. This seemingly straightforward idea has puzzled physicists for centuries. Why does time move forward and not backward? And here's where quantum entanglement might offer a surprising clue. At the heart of this mystery is entropy, a measure of disorder in the universe. According to the second law of thermodynamics, entropy always increases over time. This is why a shattered glass doesn't spontaneously reassemble itself. It's far more likely for things to move from order to disorder than the other way around. But what does this have to do with entanglement? Some physicists believe that entanglement might be the hidden force driving this increase in entropy, and by extension, the arrow of time. Imagine the universe as a vast network of entangled particles. Each time particles interact and become entangled, they create new connections, adding to the complexity of the system. Over time, these connections multiply, leading to an increase in entropy. In this view, entanglement isn't just a feature of quantum mechanics. It's a fundamental process that shapes the flow of time itself. The more entangled the universe becomes, the more disorder increases and the more time moves forward. But there's more to it. Some theories suggest that entanglement might also explain why we perceive time as moving in one direction. In the quantum world, particles can exist in a state of superposition, where they're in multiple states at once until observed. When entanglement occurs, these superpositions collapse, creating a sequence of events that we experience as the passage of time. In other words, entanglement might be the mechanism that transforms the quantum world's timeless possibilities into the linear flow of time we observe. This idea has profound implications for our understanding of the universe. If entanglement is indeed linked to the arrow of time, it means that time itself might be an emergent property of quantum interactions. It's not something that exists independently, it's a consequence of the way particles interact and become entangled. This challenges our traditional view of time as a fixed, unchanging backdrop and suggests that it's deeply intertwined with the quantum fabric of reality. Of course, these theories are still speculative and much remains to be explored, but the possibility that entanglement could explain the arrow of time is a tantalizing one. It offers a new way to think about one of the most fundamental aspects of our existence and opens up exciting avenues for future research. As we continue to unravel the mysteries of quantum entanglement, we might just find that it holds the key to understanding not just the universe but time itself. Now, let's take a fascinating leap from the cosmic to the microscopic, where quantum entanglement might be influencing life itself. This brings us to the intriguing and controversial idea of quantum biology, a field that suggests entanglement could play a role in some of the most fundamental processes in living organisms. From the way plants harness sunlight to how birds navigate across continents, quantum mechanics might be quietly at work in the natural world. One of the most studied examples is photosynthesis, the process by which plants convert sunlight into energy. At first glance, this seems like a purely chemical process, but researchers have discovered something extraordinary. When light hits a plant's leaves, the energy is transferred through a network of molecules with incredible efficiency. How some scientists believe that quantum entanglement might be the key. The energy appears to explore multiple pathways simultaneously, thanks to quantum superposition before settling on the most efficient route. This could explain why plants are so effective at capturing and using sunlight, far beyond what classical physics would predict, but the surprises don't stop there. Another area where quantum entanglement might be at play is in bird migration. Birds like the European robin are known to navigate using Earth's magnetic field, but the exact mechanism has long been a mystery. Some researchers propose that entangled particles in the bird's eyes could act as a quantum compass, allowing them to sense the magnetic field with remarkable precision. This theory suggests that entanglement might enable birds to see the Earth's magnetic lines, guiding them across thousands of miles with astonishing accuracy. Of course, these ideas are not without their skeptics. Critics argue that the warm, wet, and chaotic environment of living organisms is far from the controlled conditions of a quantum physics lab. They question whether delicate quantum states like entanglement could survive in such a noisy and complex system. After all, quantum effects are notoriously fragile, often collapsing when exposed to even the slightest interference. So, while the evidence is intriguing, it's far from conclusive. Despite the skepticism, the field of quantum biology continues to grow, offering tantalizing hints that life might be more deeply connected to the quantum world than we ever imagined. If entanglement does play a role in biological processes, it could revolutionize our understanding of life itself, blurring the line between physics and biology. It's a reminder that the quantum world isn't just a realm of particles and waves. It might also be the hidden force shaping the very fabric of life. As we explore these possibilities, one thing is clear: the intersection of quantum mechanics and biology is a frontier ripe for discovery. Whether entanglement truly influences life or not, the questions it raises are as profound as they are exciting. And as we continue to probe the mysteries of the quantum world, we might just find that it's not only the universe that's entangled, it's us too. Now, let's shift our focus to a theory that takes quantum entanglement into the realm of science fiction, or perhaps science fact. This brings us to the simulation hypothesis, the idea that our universe might be an incredibly advanced simulation, and quantum entanglement could be one of the key clues supporting this mind-bending possibility. Could it be that the strange behavior of entangled particles is evidence of a programmed reality? Let's explore this fascinating theory and what it means for our understanding of existence. At the heart of the simulation hypothesis is the idea that our universe operates like a computer program, with fundamental laws of physics acting as the code. Quantum entanglement, with its instantaneous connections between particles regardless of distance, seems to defy our classical understanding of space and time. Some theorists argue that this phenomenon could be a sign of optimization in the simulation. Just as a video game might use shortcuts to render distant objects only when needed, entanglement could be a way for the program of our universe to conserve resources, linking particles without the need for continuous communication. But how does this tie into our perception of reality? If entanglement is a feature of a simulated universe, it could explain why quantum mechanics often feels so counterintuitive. The probabilistic nature of quantum events, where particles exist in multiple states until observed, might reflect the way a simulation processes information. In this view, the act of observation could be akin to a program rendering a specific outcome, collapsing the quantum state into a definite result. This would mean that reality, as we experience it, is not fixed but rather generated on demand, a staggering idea that challenges everything we think we know about existence. Of course, the simulation hypothesis is not without its critics. Many argue that it's impossible to prove or disprove, making it more of a philosophical thought experiment than a scientific theory. Others point out that even if our universe were a simulation, it would still need to operate within some form of physical laws, which brings us back to the same fundamental questions about reality. Still, the idea that entanglement could be a glitch or feature of a simulated universe is undeniably intriguing, offering a new lens through which to view the mysteries of quantum mechanics. If the simulation hypothesis were true, the implications would be profound. It would mean that everything we perceive, our thoughts, emotions, and even the stars in the night sky, could be part of an elaborate construct. This raises questions about free will, the nature of consciousness, and the purpose of existence itself. Are we merely characters in a cosmic game, or is there something more to our reality? While we may never have definitive answers, the possibility invites us to rethink our place in the universe and the very fabric of what we call real. As we ponder these ideas, one thing is certain: quantum entanglement continues to challenge our understanding of reality in ways that are as thrilling as they are unsettling. Whether our universe is a simulation or not, the questions it raises remind us that the boundaries of science and philosophy are far from clear. And as we explore these mysteries, we might just find that the line between reality and illusion is thinner than we ever imagined. Now, let's turn our attention to a theory that connects quantum entanglement to one of the most profound mysteries in cosmology, the fine-tuning problem. This is the idea that the fundamental constants of the universe, like the strength of gravity or the charge of an electron, appear to be perfectly calibrated to allow for the existence of life. Even the slightest change in these values would make life as we know it impossible. So, how does quantum entanglement fit into this puzzle? Could it offer a natural explanation for why the universe seems so finely tuned? At first glance, entanglement might seem unrelated to the fine-tuning problem. After all, it's a phenomenon that deals with the strange connections between particles, not the fundamental constants of nature. But some theorists suggest that entanglement could play a role in shaping the very fabric of the universe. Imagine entanglement as a kind of cosmic glue, weaving together the laws of physics in a way that ensures stability and balance. If entanglement operates on a universal scale, it might help explain why the constants of nature are so precisely set. In this view, entanglement isn't just a quirk of quantum mechanics, it's a fundamental feature that underpins the structure of reality. One intriguing possibility is that entanglement could act as a kind of feedback mechanism, fine-tuning the universe over time. Just as entangled particles influence each other instantaneously, the universe might have evolved in a way that naturally selects for conditions conducive to life. This idea aligns with the anthropic principle, which suggests that the universe must have the properties it does because we are here to observe it. If entanglement plays a role in this process, it could mean that the fine-tuning of the universe isn't a random accident but the result of deeper, interconnected quantum processes. Of course, this theory is still speculative and it raises as many questions as it answers. For instance, if entanglement is responsible for fine-tuning, what determines the rules that govern entanglement itself? Is there a deeper layer of reality that we have yet to uncover? These questions push the boundaries of our understanding, reminding us that the fine-tuning problem is far from solved. But the possibility that entanglement could be part of the answer is a tantalizing one, offering a new perspective on one of the biggest mysteries in science. As we consider these ideas, it's worth reflecting on what they mean for our place in the universe. If entanglement is indeed linked to fine-tuning, it suggests that the cosmos is not just a random collection of particles but a deeply interconnected system, finely balanced to allow for the emergence of life. This perspective invites us to see the universe not as a cold, indifferent place but as a dynamic, evolving entity with its own intricate logic. And while we may never fully understand the mechanisms behind fine-tuning, the journey to uncover them continues to inspire awe and wonder. With this in mind, let's move forward to explore another fascinating theory, one that takes us even deeper into the mysteries of quantum entanglement and its implications for the nature of reality. Now, let's venture into a theory that blurs the line between science and philosophy: quantum immortality. This idea takes the concept of quantum entanglement and applies it to the very nature of consciousness and existence. At its core, quantum immortality suggests that consciousness might never truly end, but instead it persists across parallel universes thanks to the strange and interconnected nature of entangled particles. It's a mind-bending theory that challenges our understanding of life, death, and the fabric of reality itself. To grasp this concept, let's revisit the many worlds interpretation, which proposes that every quantum event spawns a new universe. In this framework, every possible outcome of a situation exists in its own separate reality. Now, imagine applying this to the survival of consciousness. If every decision or event creates branching universes, then in at least one of those universes, your consciousness continues to exist, no matter how unlikely the odds. This is the essence of quantum immortality, a theory that suggests you might never experience your own death because your consciousness always finds a universe where you survive. But what does this mean for entanglement? If entangled particles can influence each other across vast distances, could they also connect consciousness across parallel realities? Some theorists propose that entanglement might act as a bridge, linking versions of ourselves in different universes. In this view, our sense of self isn't confined to a single timeline, but is instead spread across a multiverse of possibilities. This raises profound questions about identity and continuity. Are we the same person in every universe, or do we fragment into countless variations of ourselves? The ethical and philosophical implications of quantum immortality are equally fascinating and unsettling. If consciousness persists indefinitely across parallel universes, what does that mean for our understanding of mortality? Does it diminish the significance of death, or does it amplify the value of the choices we make in this reality? And what about the moral responsibility we hold in a multiverse where every action spawns countless outcomes? These questions push us to rethink not only the nature of existence but also the meaning of life itself. Critics of quantum immortality argue that it's more of a thought experiment than a testable theory. After all, how could we ever prove that consciousness continues in another universe? Yet, even as a speculative idea, it challenges us to confront the limits of our understanding and the mysteries that lie beyond. It invites us to consider the possibility that reality is far stranger and more interconnected than we ever imagined. As we reflect on this theory, it's worth considering what it means for our place in the cosmos. If entanglement truly connects us to parallel versions of ourselves, it suggests that the universe is not just a collection of isolated events but a vast, interconnected web of possibilities. This perspective invites us to see our lives not as linear journeys but as part of a much larger, more complex tapestry. And while the idea of quantum immortality may remain speculative, it reminds us that the boundaries of science and philosophy are often far more fluid than we realize. With this thought-provoking theory in mind, let's turn our attention to another intriguing idea, one that explores how entanglement might influence the very fabric of time itself. Now, let's shift our focus to a phenomenon that seems almost paradoxical: the quantum Zeno effect. Named after the ancient Greek philosopher Zeno of Elea, who famously proposed paradoxes about motion and change, this effect reveals something startling about the nature of quantum systems. At its core, the quantum Zeno effect suggests that the act of observing a quantum system can actually prevent it from changing. It's as if the system becomes frozen in its current state simply because we're watching it. But how does this work, and what does it have to do with quantum entanglement? Let's break it down. Imagine a quantum particle, like an atom, that's in a superposition of two states, say, spinning both clockwise and counterclockwise at the same time. Normally, this particle would eventually decide on one state or the other, a process known as quantum collapse. But here's where the quantum Zeno effect comes into play. If you continuously observe or measure the particle, you can effectively stop it from collapsing into a single state. It's like repeatedly asking the particle, "Are you still spinning both ways?" And in doing so, preventing it from settling on an answer. This bizarre behavior highlights just how strange and counterintuitive the quantum world can be. Now, let's connect this to entanglement. If entangled particles are linked in such a way that the state of one instantly influences the state of the other, could the quantum Zeno effect play a role in maintaining that connection? Some researchers believe so. For instance, if one particle in an entangled pair is continuously observed, could that observation prevent the entire system from evolving or decohering? In other words, could the act of measuring one particle keep the entangled state intact, effectively freezing the system in place? This idea opens up fascinating possibilities for controlling and preserving entanglement, which could have significant implications for quantum computing and communication. But the quantum Zeno effect isn't just a theoretical curiosity, it's been observed in real-world experiments. For example, scientists have used rapid measurements to keep unstable particles from decaying, effectively extending their lifetimes. This practical application shows that the effect isn't just a quirk of quantum mechanics but a tangible phenomenon with real-world consequences. And when we consider entanglement, the implications become even more profound. If we can use the quantum Zeno effect to stabilize entangled states, it could revolutionize how we build and maintain quantum systems, making them more robust and reliable. Of course, this raises questions about the nature of observation itself. What does it mean to observe a quantum system? Does it require a conscious observer, or can any interaction with the environment trigger the effect? These questions touch on the deeper mysteries of quantum mechanics and the role of the observer in shaping reality. While we don't have all the answers yet, the quantum Zeno effect reminds us that the act of measurement is far from passive. It's an active force that can alter the very fabric of the quantum world. As we explore this connection between entanglement and the quantum Zeno effect, it's clear that these phenomena are deeply intertwined. They challenge our understanding of how systems evolve and how observation shapes reality. And while the quantum Zeno effect might seem like a strange and abstract concept, its potential applications from stabilizing entangled particles to advancing quantum technologies show just how impactful it could be. With this intriguing interplay between observation and entanglement in mind, let's turn our attention to another fascinating theory, one that explores how entanglement might influence the behavior of particles in a vacuum, a phenomenon known as the Casimir effect. Now, let's venture into another intriguing intersection of quantum mechanics and the strange behavior of particles, this time exploring how entanglement might be connected to the Casimir effect. The Casimir effect is one of those phenomena that sounds almost magical. Two uncharged metal plates placed extremely close together in a vacuum are inexplicably drawn toward each other. At first glance, it seems to defy common sense. How can two objects with no charge or obvious force between them attract one another? The answer lies in the quantum realm, and it's here that entanglement might play a surprising role. To understand the Casimir effect, we need to dive into the concept of quantum vacuum fluctuations. Even in a perfect vacuum where you'd expect nothingness, the quantum field is anything but empty. Instead, it's teeming with virtual particles that pop in and out of existence, creating a kind of quantum foam. These fleeting particles exert tiny forces, and when two plates are placed very close together, the space between them restricts the types of fluctuations that can occur. Outside the plates, however, the fluctuations are unrestricted. This imbalance creates a pressure difference, pushing the plates together. It's a subtle but measurable effect, and it's a direct consequence of the quantum nature of reality. But where does entanglement come into play? Some researchers propose that the virtual particles in the vacuum might be entangled with one another. If that's the case, the entanglement could influence how these particles interact, potentially affecting the forces at work in the Casimir effect. Imagine the vacuum as a vast, interconnected web of entangled particles, each influencing the others in ways we're only beginning to understand. This idea suggests that entanglement isn't just a property of isolated particles, but could be woven into the very fabric of space itself. The implications of this connection are profound, especially for quantum field theory. If entanglement plays a role in the Casimir effect, it could help us better understand how quantum fields behave on the smallest scales. It might even provide clues about how to unify quantum mechanics with general relativity, one of the biggest challenges in modern physics. For instance, if entanglement is a fundamental feature of the vacuum, it could help explain how space-time itself emerges from quantum interactions. This would be a monumental step forward in our understanding of the universe. Experiments have already begun to explore this possibility. By studying the Casimir effect in carefully controlled environments, scientists hope to detect signs of entanglement in the vacuum. These experiments are incredibly delicate, requiring precision measurements at the nanoscale, but they could reveal new insights into how entanglement shapes the quantum world. If successful, they might even pave the way for new technologies that harness the power of entangled vacuum fluctuations. Of course, this is still a developing area of research, and many questions remain. How exactly does entanglement influence the Casimir effect? Is it a dominant factor or just one piece of a larger puzzle? And what does this mean for our understanding of the vacuum and the nature of reality itself? While we don't have all the answers yet, The possibility that entanglement could be at the heart of such a fundamental phenomenon is both exciting and humbling. As we reflect on the Casimir effect and its potential connection to entanglement, it's clear that the quantum world continues to surprise us. From the strange attraction of uncharged plates to the mysterious web of entangled particles, these phenomena challenge our intuition and push the boundaries of what we thought was possible. And as we uncover more about these connections, we move closer to unraveling the deepest mysteries of the universe. With this fascinating interplay between entanglement and the vacuum in mind, let's now turn our attention to another captivating theory, one that explores how entanglement might be linked to the unpredictable behavior of quantum systems, a field known as quantum chaos. Now, let's shift our focus to a theory that takes us into the realm of unpredictability and complexity: quantum chaos. At first glance, chaos might seem like the opposite of order, but in the quantum world, it's a fascinating area of study that reveals just how intricate and interconnected systems can be. Quantum chaos explores how quantum systems behave in ways that are inherently unpredictable, even when the underlying laws of physics are well understood. And here's where entanglement enters the picture, adding another layer of mystery to this already puzzling field. To understand quantum chaos, think about how even simple systems can become incredibly complex under certain conditions. For example, imagine a pendulum swinging back and forth. In classical physics, its motion is predictable, but if you introduce quantum mechanics, things get much more complicated. The pendulum's behavior becomes influenced by tiny, random fluctuations, making it impossible to predict its exact state at any given moment. This unpredictability is at the heart of quantum chaos, and it's a phenomenon that appears in everything from atomic nuclei to the behavior of electrons in a magnetic field. Now consider entanglement. We know that entangled particles share a deep connection, where the state of one instantly influences the state of another, no matter how far apart they are. Some researchers suggest that entanglement might play a key role in the chaotic behavior of quantum systems. How? Well, if particles are entangled, their interactions could become so intertwined that even small changes in one particle could lead to wildly unpredictable outcomes across the entire system. This could amplify the chaotic nature of quantum systems, making them even harder to predict or control. The implications of this connection are profound. If entanglement is indeed linked to quantum chaos, it could help us better understand complex systems in nature, from the behavior of molecules in chemical reactions to the dynamics of stars in a galaxy. It might even shed light on why some systems, like the weather or the stock market, are so difficult to model accurately. By studying how entanglement influences chaos, we could uncover new principles that govern the behavior of complex systems, both in the quantum realm and beyond. One area where this theory could have a significant impact is in quantum computing. Quantum computers rely on the precise control of quantum states, but chaos introduces unpredictability that could disrupt their operations. If entanglement contributes to this chaos, understanding the relationship between the two could help engineers design more stable and efficient quantum systems. It might also lead to new ways of harnessing chaos for practical applications, such as secure communication or advanced simulations. Of course, this is still a developing field, and many questions remain. How exactly does entanglement influence quantum chaos? Is it a driving force or just one of many factors at play? And what does this mean for our understanding of the universe's most complex systems? While we don't have all the answers yet, the idea that entanglement could be intertwined with chaos is both intriguing and thought-provoking. As we explore this theory, it's clear that the quantum world continues to challenge our understanding of order and disorder. From the unpredictable behavior of entangled particles to the chaotic dynamics of complex systems, these phenomena remind us that the universe is far more intricate than we often realize. And as we uncover more about these connections, we move closer to unraveling the mysteries that lie at the heart of reality itself. With this exploration of quantum chaos and entanglement in mind, let's now turn to another captivating theory, one that revisits one of the most enduring questions in quantum mechanics, the measurement problem, and how entanglement might offer new insights into this fundamental mystery. Now, let's dive into one of the most perplexing questions in quantum mechanics, the measurement problem. This mystery lies at the very heart of quantum theory, challenging our understanding of how the universe works. At its core, the measurement problem asks a simple yet profound question. Why do quantum systems seem to collapse into a definite state when we observe them? And here's where entanglement steps in, offering a potential key to unlocking this enduring puzzle. To grasp the measurement problem, let's start with a basic idea. In the quantum world, particles don't have definite properties until they're measured. Instead, they exist in a superposition of all possible states. For example, an electron might be spinning both clockwise and counterclockwise at the same time until you measure it, and it suddenly chooses one direction. This collapse from multiple possibilities into a single outcome is what baffles scientists. Why does observation force the system to settle on one state? And what exactly counts as an observation in the first place? This is where entanglement comes into play. We know that entangled particles are deeply connected, sharing a bond that defies distance and time. Some researchers suggest that entanglement might hold clues to solving the measurement problem. Here's how: when two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. This instantaneous connection raises the possibility that entanglement could be the mechanism behind the collapse of quantum states. In other words, the act of measuring one particle might trigger a chain reaction that forces the entire entangled system to settle into a definite state. But the story doesn't end there. Some theories propose that entanglement might not just explain the collapse, but also redefine what we mean by observation. In the traditional view, an observer is a conscious being like a scientist in a lab. But in the context of entanglement, observation could be any interaction between particles, even if no human is involved. This idea shifts the focus from human consciousness to the broader concept of interaction, suggesting that the universe itself might be constantly observing and collapsing quantum states through entanglement. The implications of this theory are staggering. If entanglement is indeed tied to the measurement problem, it could reshape our understanding of reality itself. It might explain why the quantum world behaves so differently from the classical world we experience every day. And it could even bridge the gap between quantum mechanics and our intuitive sense of how the universe should work. For instance, if entanglement is the glue that holds quantum systems together, it might help us understand why large objects like tables or planets don't exist in superpositions, even though their tiny components do. This theory also has practical implications, particularly for quantum technologies. Quantum computers, for example, rely on maintaining superpositions of states to perform calculations. But the measurement problem poses a challenge. How do you keep a system in superposition long enough to use it? If entanglement plays a role in collapsing quantum states, understanding this relationship could lead to better ways of controlling and stabilizing quantum systems. It might even open the door to new technologies that harness the power of entanglement in ways we can't yet imagine. Of course, this is still a developing area of research, and many questions remain. How exactly does entanglement influence the collapse of quantum states? Is it the primary driver or just one piece of a larger puzzle? And what does this mean for our understanding of the role of observers in the universe? While we don't have all the answers yet, the idea that entanglement could shed light on the measurement problem is both exciting and thought-provoking. As we reflect on this theory, it's clear that entanglement continues to challenge our understanding of the quantum world. From the mysterious collapse of quantum states to the profound connections between particles, these phenomena remind us that the universe is far stranger than we often realize. And as we explore these connections, we move closer to unraveling the mysteries that lie at the heart of reality itself. With this exploration of entanglement and the measurement problem in mind, let's now turn to another captivating theory, one that looks to the future and examines how entanglement is shaping the next frontier of physics. Now let's shift our focus to the future, a future where entanglement isn't just a fascinating phenomenon but a cornerstone of groundbreaking advancements in physics. As we stand on the brink of a new era in science, entanglement is poised to revolutionize everything from quantum computing to our understanding of the cosmos. This theory, number 29, explores how entanglement is shaping the future of physics and what it could mean for humanity's quest to unlock the secrets of the universe. One of the most exciting areas where entanglement is making waves is in the field of quantum computing. Traditional computers rely on bits which can be either 0 or 1. But quantum computers use qubits which can exist in a superposition of both states simultaneously, thanks to the principles of quantum mechanics. Entanglement takes this a step further by allowing qubits to be deeply interconnected, enabling quantum computers to perform complex calculations at speeds that would be impossible for classical machines. Imagine solving problems in seconds that would take today's supercomputers thousands of years. From drug discovery to cryptography, the potential applications are staggering. But here's the catch: maintaining entanglement in qubits is incredibly challenging. Any interaction with the environment can cause decoherence, breaking the delicate quantum states. That's why researchers are working tirelessly to develop new ways to stabilize and control entangled systems, paving the way for practical quantum technologies. Beyond computing, entanglement is also transforming our understanding of the universe itself. In cosmology, scientists are exploring how entanglement might explain some of the biggest mysteries in the cosmos. For instance, the cosmic microwave background, the faint glow left over from the Big Bang, shows a remarkable uniformity across vast distances. How did regions of the universe that were too far apart to ever interact end up looking so similar? Some theories suggest that entanglement in the early universe could have created these connections, linking distant regions in ways that defy classical physics. If proven, this could reshape our understanding of the universe's origins and its large-scale structure. Entanglement is also opening doors to new technologies that sound like science fiction. Take quantum communication, for example. By using entangled particles, scientists are developing ultra-secure communication networks that are virtually immune to hacking. The reason: any attempt to intercept or measure the entangled particles would instantly disrupt their connection, alerting the users to the breach. This could revolutionize fields like cybersecurity, finance, and even national defense. Similarly, quantum sensors devices that use entanglement to measure physical quantities with unprecedented precision could lead to breakthroughs in fields like medicine, geology, and navigation. But the impact of entanglement doesn't stop there. It's also inspiring new ways of thinking about the fundamental nature of reality. For instance, some physicists are exploring the idea that entanglement might be the key to unifying quantum mechanics and general relativity, two theories that have remained stubbornly incompatible for decades. By studying how entanglement operates on both the smallest and largest scales, researchers hope to uncover a deeper framework that explains all the forces of nature. This could lead to a theory of everything, a single set of equations that describes the entire universe from the tiniest particles to the vast expanse of space-time. Of course, these advancements come with their share of challenges. Entanglement is notoriously difficult to study and control, requiring cutting-edge technology and innovative approaches. But the potential rewards are immense, from unlocking the secrets of the cosmos to creating technologies that transform our daily lives. entanglement is at the heart of some of the most exciting developments in modern physics. As we look to the future, it's clear that entanglement will continue to play a central role in shaping our understanding of the universe. Whether it's powering the next generation of quantum computers, revealing the hidden connections in the cosmos, or inspiring entirely new fields of research, this phenomenon is a testament to the boundless possibilities of science. And as we push the boundaries of what's possible, we're reminded that the universe is full of surprises waiting to be discovered. With this glimpse into the future of entanglement, let's now turn to our final theory, one that reflects on the profound implications of this phenomenon for our understanding of reality itself. As we reach the final theory, let's take a moment to reflect on what quantum entanglement truly means for our understanding of the universe, and for us as humans trying to make sense of it all. Quantum entanglement isn't just a scientific curiosity. It's a phenomenon that forces us to confront the limits of our knowledge and rethink the very nature of reality. This theory, number 30, invites us to step back and consider the philosophical implications of living in a universe governed by such strange and seemingly inexplicable rules. At its core, entanglement challenges one of the most fundamental assumptions we have about the world, that objects exist independently of one another. In our everyday experience, we see things as separate and distinct. A chair is a chair and a table is a table. They don't influence each other unless something acts upon them. But entanglement tells us that, at the quantum level, particles can be deeply connected in ways that defy this intuition. They can influence each other instantaneously, no matter how far apart they are, as if space and distance don't matter. This raises profound questions about the nature of reality itself. Is the universe fundamentally interconnected in ways we can't yet fully grasp? And if so, what does that mean for our understanding of cause and effect, or even free will? These questions aren't just academic. They touch on the very essence of what it means to be human. For centuries, we've relied on science to explain the world around us, to give us a sense of order and predictability. But entanglement reminds us that the universe is far stranger and more mysterious than we ever imagined. It pushes us to confront the limits of our understanding, to acknowledge that there are aspects of reality that may always remain beyond our reach. This can be both humbling and exhilarating. On one hand, it's a reminder of how much we still have to learn. On the other, it's an invitation to keep exploring, to keep asking questions, and to embrace the wonder of the unknown. Entanglement also challenges our notions of objectivity. In classical physics, the universe exists independently of the observer. But in the quantum world, the act of observation seems to play a crucial role in determining the state of a system. This has led some to speculate that consciousness itself might be intertwined with the fabric of reality. While this idea remains controversial, it opens up fascinating possibilities for how we think about the relationship between mind and matter. Could our perceptions shape the universe in ways we don't yet understand? And if so, what does that mean for our place in the cosmos? These philosophical questions don't have easy answers, but they highlight the profound impact entanglement has had on our worldview. It's not just a tool for building quantum computers or exploring the cosmos, it's a lens through which we can examine the deepest mysteries of existence. As we continue to study entanglement, we're not just advancing science, we're also grappling with questions that have puzzled philosophers for centuries. What is reality? What is our role in the universe? And how far can human understanding truly go? In the end, entanglement reminds us that the universe is far more complex and beautiful than we can imagine. It challenges us to think beyond the limits of our current knowledge and to embrace the possibility that some mysteries may never be fully solved. But that's part of what makes science so exciting. It's a journey of discovery, one that constantly pushes us to expand our horizons and explore the unknown. As we close this exploration of 30 theories about quantum entanglement, let's carry this sense of wonder with us, knowing that the universe is full of surprises waiting to be uncovered. As we bring this journey through 30 theories about quantum entanglement to a close, it's clear that this phenomenon is more than just a scientific curiosity. It's a gateway to understanding the universe in ways we never thought possible. From Einstein's spooky action at a distance to the mind-bending possibilities of wormholes, parallel universes, and even the role of consciousness, entanglement has reshaped our understanding of reality itself. Each theory we've explored has peeled back another layer of the cosmic mystery, revealing a universe that is far stranger, more interconnected, and more beautiful than we ever imagined. Quantum entanglement challenges us to rethink everything we thought we knew about space, time, and the nature of existence. It forces us to confront the limits of our knowledge and to embrace the idea that some questions may never have definitive answers. But rather than being discouraging, this uncertainty is what makes science so thrilling. It's a reminder that the universe is full of surprises waiting for us to uncover them. Whether it's through the lens of black holes, the potential of a quantum internet, or the philosophical implications of a holographic reality, entanglement continues to push the boundaries of what we thought was possible. So, what does all of this mean for us? It means that the universe is far more complex and interconnected than we can fully comprehend. It means that the act of observing and questioning is just as important as the answers we find. And it means that the journey of discovery is never truly over. As we continue to explore the mysteries of quantum entanglement, we're not just advancing science, we're also deepening our understanding of what it means to exist in this vast, mysterious cosmos. Now it's your turn to join the conversation. What do you think about these theories? Do you believe entanglement holds the key to unlocking the universe's deepest secrets? Or do you think there are still pieces of the puzzle we're missing? Share your thoughts in the comments below. We'd love to hear your perspective. And if you're as fascinated by this topic as we are, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the wonders of the universe. The cosmos is full of mysteries, and together we can keep uncovering them. Thanks for watching, and until next time, keep wondering, keep questioning, and keep exploring.